Today, we want to take a step back and think a little bit more about writing proofs. We're going to start by just observing that we have a linearly dependent set of vectors. Let's suppose we have this linearly dependent set of vectors. And let's write down what we know about this linearly dependent set. So, some observations. When it comes to writing proofs, we're going to have to take a piece of information that we're given and decide how we're going to use that information to get what we want. There's no proof going on right here. We're just taking the given piece of information and writing down what we know or what this piece of information tells us. And then we can decide in a context of a proof, which would be the most useful. So suppose this set of vectors is linearly dependent. One thing that this means is that one of the vectors is a linear combination of the other vectors. So this was our first kind of casual definition of linear dependence. One of the vectors is a linear combination of the other vectors. Specifically, if one of the vectors is linear combination of the other, well, not specifically because we don't know what the relationship is. But moreover, if one of the vectors is a linear combination of the others, that means they're all linear combinations of each other. If we can write V3 as a combination of V1 and V2, then V1 is also a combination of V2 and V3, and similarly V2 is a combination of V1 and V3. So we could kind of clean this up saying or we could expand on this and saying they're combinations of each other. So if V3, for example, when we go to find this combination, we would set up an augmented matrix, and V3 would be the third column. And so we would be solving, we would be writing V3 as a combination of V1 and V2. So if we had something like V3 is equal to 4V1 minus 5V2, we could also solve this for V1. We could write V1 as a combination of V2 and V3. So we can also say that V1, this is not the combination that we would come up with if we were solving an equation, but we could say V1 is 5/4 V2 minus 1/4 of V3. Just put the 4 over here, the 4V1 over here, and then divide by -4. Put the V3 over here, divide by -4. Oh, divide by -4. So we could also solve for V2. We divide by 5 and move things around. So there's a dependence relation. But this was kind of our casual way of understanding what linear dependence was. It was the first thing we talked about. One of the vectors is a linear combination of the others. So there's one of these vectors that we don't need. We can get rid of it and just keep the other two if they're linearly independent. So the reason that this is useful is that once we understand that one of the vectors is a linear combination of the others, we can think about getting rid of that vector. So we can get rid of the extra vectors. So we can think of this as, this is useful because this allows us to get rid of the extra vectors. If V3 is just a combination of V1 and V2, I don't really need V3. I can just, anything I wanted to build with V3, I can just build a V3 out of V1 and V2, and I can get the same combination. Now, this is not a very precise description of what's going on. It's a good way for us to think about things, but it lacks precision. So that's when we came across the next thing, which was the definition of linear dependence. So we refined this idea to the homogeneous equation thing. So if this set of vectors is linearly dependent, then the homogeneous equation x1 v1 plus x2 v2 plus x3 v3 equals 0 has a non-trivial solution. So once again, I want to take this opportunity to remind you that you can't just say there is a non-trivial solution. You have to be referring to a homogeneous equation. So there has to be a homogeneous equation already in evidence. If there isn't one, then you have to write it. If I said this set of vectors is linearly dependent and you just said that means there's a non-trivial solution. That's why I kept saying a non-trivial solution to what equation? What equation are you talking about? All we have is a set of vectors. There's no equation. So what are these solutions you're talking about? If you just said the homogeneous equation has a non-trivial solution, I usually let that slide, but I could be fully justified in saying, what homogeneous equation? We're looking at a set of vectors. What equation are you talking about? But if you told me that this homogeneous solution had a non-trivial solution, or just this equation, which is clearly a homogeneous equation, has a non-trivial solution, that would be a complete response. So the other way we can describe this, the non-trivial solution thing, another way to phrase this same idea is to say there are scalars not all zero such that scalars x1, x2, x3, not all zero such that x1 v1 plus x2 v2 plus x3 v3 is equal to 0. So that's the x1, x2, x3, not all 0 is the non-trivial solution to the homogeneous equation. So the reason I want to point both of these out is that a lot of us are still just kind of like taking bits of these definitions and putting them in our explanations. And that makes for incomplete explanations. You have to have all the pieces there. You can't just say there's a non-trivial solution without an equation. Specifically, if you're going to say non-trivial solution, you need to be looking at a homogeneous equation. So if you're going to bring up scalars that aren't all 0, there has to be some equation running around. One of the things that we always want to go after is pivots in a matrix. Right now, there is no matrix. I have a set of vectors. S is a set of vectors and not a matrix. So one of the things that we want to note is that S is a set of vectors and not a matrix. Since S is a set of vectors and not a matrix, it doesn't make sense to use S in an equation. like the capital letter S in an equation. So when we write Sx equals 0, this is claiming that S is a matrix. This equation doesn't make any sense, even though it makes I can see what you're going for. This equation doesn't make any sense because S is a set of vectors and not a matrix. S is not a matrix. We can't just use S as a matrix. You might say AX equals 0 has a non-trivial solution, in which case I would say, what is the matrix A? If we want to say something about pivots or a matrix equation, we have to tell our reader what matrix we are talking about. So we could observe that the matrix we wouldn't have to write the matrix, but the matrix V1, V2, V3 does not have a pivot in every column. If we want to talk about a matrix and pivots, we're going to have to define what matrix we are talking about. What matrix does not have the pivots? Because S is not a matrix. S does not have any pivots. S is a set of vectors and not a matrix. I can't use it in an equation. And we should also note that S does not have pivots because S is not a matrix. S does not have pivots because S is not a matrix. We're in a similar situation if we want to start talking about a linear transformation, which is something else that we can talk about. We could say that the linear transformation has a non-trivial kernel, but we don't have a transformation in play. We've got a set of vectors. The linear transformation defined by matrix multiplication by this matrix has a non-zero kernel. That would be pretty far to go. But once again, we wouldn't want to say anything about the linear transformation because there isn't one here. All we have is a set of vectors. All right. So we have an idea of what it means for a set to be linearly dependent. Let's look at one of the kind of classic proofs of linear algebra, classic theorem that we as math teachers always make students prove. So let's talk about a classic linear algebra proof. Let's suppose that we start off with a linearly dependent set of vectors, and if T maps Rn to Rm is linearly dependent in Rn, and T maps Rn to Rm is a linear transformation, then the set of images of this linearly dependent set under a linear transformation is also linearly dependent. So that is the set of images of a linearly dependent set under a linear transformation is linearly dependent. This typically shows up as a homework problem when you have talked about linear independence and linear transformations. So what we want to do is take the two pieces of information that we're given. We're given that S is a linearly dependent set, and we're given that T is a linear transformation. And we want to take everything that we know about those two givens and somehow combine them to get what we want, the conclusion that this set of vectors is linearly dependent. I'm going to give this set of vectors a name. So I'm going to say this is the set of images of all the vectors in S. So we're given information and that tells us some stuff. We have to look at what we want to show. And then we'll figure out how to take the given information and combine it together to get what we want to prove. So look at the given information that we have. So we have that S is linearly dependent. So here we have this is one of our givens. This tells us stuff. See on the previous page. That tells us a bunch of stuff. Our other given, our second given, is that T is a linear transformation. There's given number 2. So one of the things that we're going to want to make sure that we do when we're writing our proof is that at some point we have to say, when we make a claim, we have to refer to the fact that S is linearly dependent, because that's one of the givens. If we write a proof and we have not made reference to one of the pieces of given information, then we've either missed something and we need to fix our proof, or that piece of information was not necessary to begin with. This is pretty efficient. There's two pieces of given information. At some point, we better be saying, since S is linearly dependent, and at some other point, we better be saying, since T is a linear transformation. Otherwise, I'd be able to not to take those pieces out of my theorem. So given number 1 has all the stuff that we listed on page 1. That's a consequence of the fact that this set of vectors is linearly dependent. Given number 2, we should think about what that means. So T is a linear transformation. That's our second given. So let's talk about what that tells us. So let's see, it's a linear transformation. That means we can implement it with a matrix multiplication. So T of X equals A times X for some M by N matrix A. If T is a linear transformation, then there is a matrix that implements that map. That's what makes a linear transformation, or it's one of the things that makes a linear transformation. We also know from the definition of linear transformations that T respects scalar multiplication and vector addition. So T respects scalar multiplication and vector addition. That means that the image of a combination is the combination of the images. Image of a combination is combination, the same combination of the images. So the image of a combination is that same combination of the images. So at a certain point, we're going to have to use one of these pieces of information, either the matrix bit or the fact that T respects scalar multiplication and vector addition. So we can see what's going to be relevant, because for the definition of linear transformations, this respecting scalar multiplication and vector addition seems to be a thing. It respects linear combinations, and one of our pieces of information about a linearly dependent set was about a linear combination. One of the vectors is a linear combination of the others. And we also have this, the homogeneous equation says this linear combination can be zero. Even there's a non-trivial linear combination of the vectors that's equal to the zero vector. Oh, which reminds me of another thing. T is a linear transformation. That means that the image of the zero vector will be the zero vector. I knew there were three. I was just blanking on the third one. So now we can see, we can start combining these things, and we can see how our proof is going to go. We want to show that this set of vectors, the set of images, is linearly dependent. I want to show that this, that T of S, the set of images, I want to show that one of those vectors is a linear combination of the others. I want to show that homogeneous equation involving all those vectors has a non-trivial solution. I want to show that the matrix made up of all those vectors does not have a pivot in every column. And there's other ones. There's something else. Oh, that's what I did. So I want to pick one of those things that I can show using the given information. Since we're starting off with a linearly dependent set, that makes us think one of the vectors is a linear combination of the others. We're running them all through a linear transformation which respects those linear combinations. So that means that one of the vectors in the set of images is going to be that same linear combination of the vectors in S. So now we can see how we're going to use the given information in the given information 1 and given information 2 to get what we want. So that's our third thing. This set of vectors is our target. This set of vectors is linearly dependent, is what we want. Trying to show that 1 and 2 imply 3. So what we're going to do is we're going to say one of these the vectors in S is a linear combination of the others. The set of, when I take the image of that combination, I get that same combination of the images. Therefore, one of the images in T of S is a linear combination of the other vectors in T of S. We're also going to use the fact that T of 0 is equal to 0 since T is a linear transformation. So let's write down what we know. So since S is linearly dependent, linearly dependent, one of these vectors is a linear combination of the others. Let's say that in a more concrete way. Let's use the homogeneous equation business. That means there are scalars, not all 0. So since this set is linearly dependent, there are scalars looks like there are P of these vectors. So C1, C2, up to CP, not all 0, such that C1 V1 plus C2 V2 plus CP VP is equal to 0. A non-trivial linear combination of these vectors will result in a 0 vector because they're linearly dependent. That means one of these vectors is a linear combination of the others. Since the C1 through CP are not all 0, that means I'll be able to divide by whatever one is not 0. Subtract everything onto one side, divide by the coefficient that's not 0, and then we have our linear combination. Now we're going to use the fact that the image of this combination is just going to be the same combination of those images, and the image of 0 is 0. And that's because T is linear. So we'll say, since T is linear, T of 0 is equal to 0. And the image of this combination is that same combination of the images. Oops. So now we can go back to look at this equation, this linear combination, where the scalars are still not all 0, and this image is equal to 0 because the image of the 0 vector is the 0 vector. So now we can conclude there are scalars C1 through CP, not all 0. Therefore, there are scalars C1 through CP, not all 0, such that C1 T of V1 plus C2 T of V2 equals 0. Therefore, we can see that the set of images T of S is linearly dependent. And then we're done. That's what we wanted to show. The idea is that when we're trying to write a proof, we have to look at what we're given. We have to look at what we're given and decide what that tells us, all the different things that it tells us. We have to look at what we want to show, and we have to think about all the things that would allow us to show that. Then we got to think about how to combine the givens to get what we want to prove. Any questions? All right, one of the reasons that we want to do this is that, so this is your first course in linear algebra. And of course, when I say this is your first course in linear algebra, everybody's like, oh no, there are others. And for some of you, there will be. Some of you are going to be math majors and you're going to have to take another class in linear algebra. You're going to have to take a bunch of algebra classes. You're going to have to take a class called real analysis. And during real analysis, you'll just start thinking, hey, is this just calculus? And then the instructor will be like, oh, quiet you, and this is clearly real analysis. It says it right on the book. Then you'll take a class called complex analysis, and you're like, oh, dude, is this just calculus, but with complex numbers? And your professor will be like, oh, quiet you. Then you'll take a class called combinatorics. And you think, hey, are we just counting in this class? And your professor will be like, oh, quiet you, it's very fancy, combinatorics. But when you're a graduate student, you're going to take more classes or an upper division math student at least, you'll be taking more classes in algebra, and that might include some more linear algebra. And that linear algebra course is probably going to be super proof heavy. You've had one course to get used to the computations that you make, and then you do the course again with a focus on the proofs. So we start with giving you some proofs in your first course in linear algebra. The place that you would want to be as far as this one particular proof goes, we actually have the proof, so I don't know why we have to go around rehashing it all the time, but we do. The place you would want to be is to look at this linearly dependent set and say, one of these is a linear combination of the others. The linear transformation will respect that linear combination. And so one of the vectors, one of the images is going to be a linear combination of the other images. Then it just comes down to writing a bunch of proofs and learning math proof writing style. And it's just developing the style guide. All right, let's pause the video here. And I wanted to talk about this because it comes up. I get emails about questions whenever there's a homework problem that says prove that or show that. Show that tends to be a little more subtle than prove. If you see a problem that says explain, you're just like, oh, okay. Or show that, that's a little more serious. But if it says prove, then you're like, oh no, this is super serious. Do I have to do that statement and reason thing that I did back in geometry? And then your instructor will be like, oh, yeah, but this time in essay form. And you're like, oh, I took math, so I wouldn't have to write essays. All right, let's pause the video here, and then we'll go back and talk about some eigen stuff.